Hi guys, this time we're going to learn about how to solve a linear differential equation using a method of integrating factors. First, let's look at a formula of a linear differential equation's first order is in the form of y prime plus p of t y equals q of t. Given an initial solution, an initial values is t0, y0. And this is the first equation that we're considering in these lectures. And then as we know that before trying to attempt to solve this equation, we want to see if this equation, this IVB problem, will have a unique solution or not. Okay, and the existence and unique solutions here is very simple. That means you are guaranteed to have a unique solutions when P of t and Q of t are both continuous on A to B. Also, T0 is in this interval from A to B, regardless values of Y0. So that means Y0 can be any values. As long as T0 is in this interval in which both P of t and Q of t are continuous, then this IVP number 1 will have a unique solutions. Let's look at an examples. Consider an equation y prime plus 1 over ty equals square root of t with initial condition 0, 1. Then first, what is P of t is 1 over t is continuous everywhere but 0. Q of t square root of t is continuous from 0 to infinity. Then at t equals 0, P of t is discontinuous. Thus, the second equation here does not have a unique solutions. Now let's look at the general form of a linear differential equations. Y prime plus P of t y equals qt. Our goal is we want to solve for these equations. Then using the method of integrating factors, the idea is you want to multiply both sides by mu t, which is an arbitrary functions. It is an unknown functions, and the goal is you want to find this unknown mu functions such that the left-hand side of the functions here will be equals the derivative of the products of mu times y. And back to calculus 1, we know that mu times y, derivative of mu times y equals mu prime times y plus mu times y prime. And if you look at the equations after multiplying mu of t, and if you want to force the left-hand side with this derivative of the products, as we notice that we have two terms are identical on both sides, which is mu y primes here. They're identical, so that means the only term that we should force to equal each other is mu p times y equals mu prime y. Knowing that, we can rewrite the two terms that we want to force to be equal to each other is this, and then y can be cancelled out, and then you can use separable equations to solve for mu, because you can actually divide mu from both sides to separate mu and y. Mu and pt, I'm sorry. Okay, so once using separable equations, you can solve for mu because that's the goal. We want to find mu of t. And the result give you mu of t will be equals e to the integral of b of t times dt. B of t is the functions that is given in our differential equations. Alright, once we have mu of time, then we know that go back to our goal, we want to create a mu function such that the derivative of the products here equals the right hand side. So the left hand side will be the products of the derivative of the product, and then is equals the right hand side after we multiply mu to the whole function, so whole equations, right? And it's just easy now to see that in order to solve for y, you just need to integrate both sides to get mu times y on the left side, and you have an integral on the right side. To solve for y, you just need to divide mu t by both sides. This will give you a formula of the functions of a linear first-order differential equation using the method of integrating factors. As I say, mu t is a function that we can find by taking e to the integral of p of t times dt. And the integrals mu times qt dt can be determined using some of the methods that we learned in Calculus 2, or in case that it's impossible to find this integral, you just leave it in this integral term. All right. In case that we have an IVV problem using this method of integrating factor, in order to find c, you just need to plug t0 into all the t and y0 to the left side, and the integrals here will be the integration from t0 up to t. And then notice that functions inside the integrals is replaced. We replace t by s as a dummy variable because you don't want to have a repeated independent variable in this integrand and also in this integral value. Okay. All right. Now let's look at an examples trying to solve this IVP using the method of integration factor. First, existence and uniqueness. P of x is 2 to the x, which is continuous everywhere but R. Q of x is e of x, which is continuous everywhere. That means this IVP problem here has a unique solution because t0 belongs to an interval which p of x and q of x are both continuous, because p of x continuous as 1 and q of x is also continuous as 1. Alright, so we are guaranteed to have a unique solution. Now go ahead and the first step is solving mu of t. So mu of t is going to be equals e to the integrals of p of t, which is 2x, and then doing some integrations, you get mu of t equals x squared. And once you have mu of t, you can use a formula earlier to figure what is the general solutions for these equations, which is c over mu of t plus 1 over mu of t times to the integral of mu of t times q of t dx. Now, next question is, these integrals here, is possible to find the antiderivative for this function x squared times e to the x. And let's do that separately. So we use integration by parts, u equals x squared dv to ex, and using the formula of integration by part, these integrals here become this term. And now again, we still have another integral to solve or to find. Then again, we use integration by parts, mu equals x, dv equals ex, and we get to the answer for this integral, which is x times e to the x minus e to the x here. Put everything together, you should have y equals c over x squared plus 1 over x squared e to the x minus 2, x e to the x minus e to the x. And putting the initial values, you can solve for c equals e to the 2 minus e. So you plug 1 into all the x's and 2 into the y, and you can solve for c here. Then we can achieve our final solutions, unique solution for the differential equation given that initial point.